Action.
Action. Okay, so we're going to have a think about forces in the nucleus and try and use that to understand about the binding energy of the nucleus. So this is like our model of a nucleus. This is that tiny little pinprick at the centre of an atom. It's got all the mass and all the positive charge jammed into some incredibly dense little piece of space. The particles that we've got in there are protons and neutrons. What do we know about forces acting inside the nucleus?
Repulsion.
Positive. What do we call that?
Electrostatic repulsion.
Electrostatic repulsion, or
Attraction.
another way of saying that is Coulomb repulsion, is often the word you'll hear in the nucleus. So the electrostatic force, the Coulomb repulsion, acts between protons. And what else do we know about that force? Like what's the range of that force? What's the distance over which that force acts? Like how close does one proton have to be to another before it starts feeling that? Quite far.
Yeah, we're looking for measurements.
Quite close.
Something like that.
Really not committed. Next to each other? It's further than next to each other.
Not next to each other.
Safe standing distance.
Safe standing distance is further than a safe standing
The
distance.
2 meters. Social distancing.
More than social distancing. It's infinite.
Wait, what?
Oh
Is
yeah.
that inverse square law?
It's an inverse square law. It's exactly the same as gravity. It's an inverse square law.
You
So
always feel it, but you just
we
don't.
say that the
What?
Coulomb
No.
repulsion is an infinite range force, so that force acts over an infinite distance. So this proton here is going to be repelling this one really strongly, these ones a little bit less strongly, and then these ones even less strongly, and this one kind of least strongly. And so the further away particles, charged particles, are from each other, the smaller that Coulomb repulsion. But it's an infinite range force, so it's going to act on all of them. They're all pushing each other apart.
How do we know that the force is infinite range?
Yeah, sure.
Do we just go, oh yeah?
And
It's got to be about
Are
infinite.
we going to calculate forces on different protons? Acting on them?
I guess probably what they've done is got charged things and they've moved them apart and measured the force between them, and they've kind of extrapolated that it's going to be like that force falls off according to the inverse square law. Like,
But
I don't know if they've found charged objects on opposite sides of the universe and measured the force between them. It's going to be negligible, but I guess they've extrapolated that result.
Wait,
Good
so
question.
The
it's not
predict.
just contained in the
Can we even say what I say?
No.
Oh.
Why does this not kind of factor in when we're thinking about forces between atoms? Why don't we worry about that when we're talking about forces between atoms? Why don't the atoms push each other apart?
Well, they do.
They're all naturally charged.
They're overall neutral, right? They've got electrons as well. Nice. And so we're mostly seeing this just acting within the nucleus, and once we get outside the nucleus, there's that like shielding from the electrons that gives it an overall neutral charge. What about, so these are all pushing each other apart. Is the nucleus falling to pieces? So what do we know must be in there as well? These are being pushed apart, but they're not moving apart.
Attraction.
There must be an attractive force that's holding them together. Like the net force has to be zero because they're not going apart, they're not going together, right? And so there must be another force in here, and all these protons are pushing apart, and they're really close to each other. Like these particles are practically touching. Like how big's that force going to be?
Small.
How big?
Is it
Small.
big enough to oppose the
Oh,
Times
electrostatic?
10 to the negative.
So-
And so
equal.
it's like a really strong force, and it acts inside the nucleus. So we're going to call it the nuclear strong force.
That's cool, man.
Nuclear strong force.
And the nuclear strong force acts between all of the nucleons in the nucleus. So it acts between neutrons and protons and protons and protons. But just between protons and protons, it's not enough to prevent them from being pushed apart. So we have to have neutrons in our nucleus because they have got the nuclear strong force, but they don't have the Coulomb repulsion. And that's why you'll see when you look at the periodic table that like every element, as you go further up the periodic table, it's got more, the ratio of neutrons to protons gets higher and higher. Like for gold, we had 108 neutrons to only 79 protons. Like there's quite a lot more than twice as many neutrons, and that's just to make that nucleus stable. And the nuclear strong force is not like the Coulomb repulsion, it's a short range force. So the nuclear strong force only acts on the nearest neighbour nucleons. It's got like a range of about the size of a nucleon. A nice way of thinking about it is like a rubber band force. And so if we move those nucleons further away from each other, and there's a rubber band around them, what happens to the rubber band?
Snaps.
Eventually it snaps, but first
Stretches.
it stretches and the force holding them together gets
Larger.
larger. And we move them a bit further apart and the force gets, and then the rubber band snaps and they're able to fly apart. And so the nuclear strong force is a really bizarre force. It gets stronger and stronger as they move apart and then suddenly zero. So it's a short range force that acts between the nearest neighbour nucleons.
Well,